In this course, we're going to study an algebraic structure called groups. But before we delve into a formal study of groups, we're going to spend several classes investigating examples of groups. And so here's one such example that we'll study today. It's the number system Z7. So Z, remember, stood for the set of integers, but Z7 is similar but different. One big difference is that Z7 only contains, well, appropriately 7 elements: 0, 1, 2, 3, 4, 5, and 6. So there's 7 elements only in Z7, so it's a finite set. But just like we do with integers, we can add, multiply, subtract in Z7, but rather than using a number line, which is typically how we think of as operating in the integers, what we have here is what's commonly known as the Z7 clock. We use the word clock because it, as you'll see, it resembles how clocks operate. In fact, you can think of our typical clock as being Z12, but let's work in Z7. So let's do some computations using the Z7 clock. So for example, how do we do 1 plus 3 in Z7? Well, 1 plus 3 means we start at 1 and move 3 units clockwise. So 1, 2, 3, and we end up at 4. So therefore, 1 plus 3, not too surprisingly, is 4. To make it a little more interesting, let's do another calculation. This time, let's look at 5 plus 4. So how do we do 5 plus 4? Well, we start at 5, and we go 4 units clockwise. 1, 2, 3, and 4. And therefore, 5 plus 4 is equal to 2. Now that's how we can add in this number system Z7. We can also subtract. So let's try 2 minus 6. What does that mean? Well, that means we start at 2, and rather than going to plus 6, we're going to minus 6. So we're going to go counterclockwise 6 units. 1, 2, 3, 4, 5, and 6. And we end up at 3. So 2 minus 6 in this number system is 3. And let's do one more calculation, which involves multiplication. So how about 3 times 5? Well, 3 times 5 we know is 15, but 15 is not one of the 7 numbers in Z7. So how do we do 15? Well, how do we view this? Well, we can think of 15 as 0 plus 15. Now that means we start at 0 and move 15 units clockwise, since we're adding 15. So rather than drawing the arrows, I'll just start here and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So after 15 units going clockwise, we ended up at 1. So we conclude that 3 times 5 is equal to 1 in Z7. And I highlight that computation, 3 times 5 equals 1. That's an important calculation. We think of 3 and 5 multiplying together and in a way canceling each other to give us a product of 1. And because of that, we say that 3 and 5 are multiplicative inverses of each other in Z7. They are multiplicative inverses of each other in Z7. And again, I say they cancel each other in Z7 under multiplication. And this calculation is very much analogous. If we think about 3 times 5 equals 1 in Z7, it's very analogous to saying, say, 1/5 times 5 equals 1 with real numbers, or 3 times 1/3 equals 1 with real numbers. And so when two numbers multiply together to be 1, we think of themselves as canceling each other out under multiplication. And therefore, we call that pair, 3 and 5 in this case, multiplicative inverses of each other in Z7. Now, please pause the video and work on day 4 classwork. And afterwards, we will review some of the exercises and ideas. Here's a subtle yet important distinction. Let's think about 16 and 30. When we view them in Z, in other words, when we view them as integers, then 16 and 30 are certainly different integers. So in Z, they are unequal to each other. However, when we view them in Z7, and when we reduce them in Z7, they both reduce to 2, as we saw in the classwork, and therefore we say that 16 and 30 are equal to each other in Z7. So when we study these numbers and number systems, it's really important to specify which number system we're in, especially when we talk about equality. Now, speaking of equality, here are a couple of notations. Now, we've been saying A is equal to B in Z7, and that's typically a notation that we'll continue to use. Oftentimes in mathematics, we say A is equal to B, parentheses, mod 7. And those mean exactly the same thing. I'll tend to stick with this notation, but you might see A equals B mod 7 in other contexts, particularly in number theory. So I just wanted you to see both phrases, and they mean the same thing. Now let's talk about problem 4 in the classwork. There we were given a pair of huge numbers, but notice that B is 70 more than A. And therefore, those two numbers are equal to each other in Z7. Once again, because B is 70 more than A. So whatever A reduces to get from A to B, we just go around the Z7 clock 10 full revolutions. That's like adding 70 in Z7, and the value stays the same. Now, here's a generalization of that particular example. So if we have a pair of integers A and B, then to say that they are equal to each other in Z7 means that the difference between A and B is a multiple of 7, such as 70. Another way to say that, using the language of divisor, is that 7 is a divisor of A minus B, the difference A minus B. Now, a special case of this that we often see is when B is equal to 0. Then the above relationship becomes A is equal to 0 in Z7, means that 7 is a divisor of A, or A is a multiple of 7. And so all the integers A that are equal to 0 in Z7 are precisely the multiples of 7. So 0, 7, 14, 21, 28, etc., as well as their negatives. Now, there is nothing special about 7 here at all. We could have said the same thing with Z9, Z12, Z15, and we would just replace 7 with 9, 12, 15, or any modulus for that matter. And so this property is true in any Zm just by replacing 7 with m. In other words, we can say that A is equal to B in Zm is the same as saying m is a divisor of the difference A minus B. That would be the generalization. Instead of using 7, we can use m. Now let's look at problem 7, in which we studied the number system Z15. So that has 15 elements from 0 to 14. And the key question we want to ask is which of the elements in Z15 have multiplicative inverses. In other words, a pair of numbers that multiply together to be 1. And so let's go through each element in Z15 and see if each of these elements has a multiplicative inverse. Now first, 0. 0 times anything is 0. So we'll never get 0 times another element equals 1. So 0's out. What about 1? Well, 1 times 1 is equal to 1. So 1 is its own inverse. So we're good to go with 1. What about 2? Well, 2 times 8 is equal to 1 in Z15, because 2 times 8 is 16, which is 1 more than 15. So we can put checks next to 2 and 8. Now let's think about 3. Well, 3 times 0 is 0, 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15, which is back to 0. And then 3 times 6 is 18, which is 3. 3 times 7 is 21, which is 6. And so we see that we're stuck in this any multiples of 3 when we reduce in Z15. We end up with either 0, 3, 6, 9, or 12. And we're kind of stuck in that loop. So 3 times any element in Z15 can only give us 0, 3, 6, 9, and 12. In particular, we'll never get a 1. So 3 does not have a multiplicative inverse. What about 4? Well, 4 is its own multiplicative inverse because 4 times 4 is 16, which is 1. So 4 is good to go. Now 5 is very similar to 3. If we think about multiples of 5 in Z15, we only get 0, 5, 10, 0, 5, 10, on and on. We'll never get a 1. And I'll leave it up to you to see that multiples of 6 will never give us 1. How about 7? Well, 7 times 13 is 91, which is 1 more than 90, which is a multiple of 15. So 7 times 13, that's a multiplicative inverse pair. So 7 and 13 are good to go. We already checked off 8. 9, once again, multiples of 9 will only give us, and I'll leave this up to you to check, 0, 3, 6, 9, 12. And so we'll never get a 1. Multiples of 10, we'll never get a 1 again. I'll leave you to check the details. 11 is its own multiplicative inverse. So 11 times 11 is 121, which is 1 more than a multiple of 15. So 11 is good. 12, again, another way to think about 12 is that 12 is negative 3. I'll write a little equals negative 3 in Z15. So multiples of 12 is the same as multiples of negative 3. And multiples of negative 3 will only give us negatives of these, which are 0, negative 3 is 12, negative 6 is 9, negative 9 is 6, negative 12 is 3. Once again, we never get a 1. We already checked off 13 and 14, and in fact, I'll put a check. We can think of 14 Well, 196 is one more than a multiple of 15, but we can also think of 14 as -1 times -1 in Z15, and therefore equal to 1. And so those are the elements in Z15 with multiplicative inverse, and we'll do a little more summary in the next slide, but I'd like to highlight 1, 4, 11, and 14. These are elements whose multiplicative inverse is itself. And for that reason, we say that 1, 4, 11, and 14 are self-inverses in Z15. Whereas 2 and 8, that's a multiplicative inverse pair. Neither is a self-inverse because they don't multiply by itself to produce a 1. And so once again, we say that 1, 4, 11, and 14 are self-inverses because its multiplicative inverse is itself. So here's the summary of the calculations that we just did in Z15. The elements in Z15 with multiplicative inverses are 1, 2, 4, 7, 8, 11, 13, and 14. And all the others are those without multiplicative inverses. Now, it would be nice if we don't have to go through the kind of calculation we just did, if there is a quicker way to determine whether an element of Z15, for instance, has a multiplicative inverse or not. Is there some characteristic that's shared by these besides the fact that they have multiplicative inverses? And so let's see. Well, if we think about 4, for instance, we realize, for example, that 4 and 15 are relatively prime. They do not share any common factor besides 1. And then we saw that 4 has a multiplicative inverse in Z15. What about the other elements in this row? What about 8? Well, 8 is also relatively prime to Z15. 13 is relatively prime. In fact, all of these are relatively prime to Z15, which is much easier to determine than actually finding their multiplicative inverses. And does it go the other way around? For instance, we saw that 6 does not have a multiplicative inverse. What do we know about 6 and 15? Their GCD is 3. It's certainly not 1. 6 and 15 are not relatively prime, and therefore we saw that 6 does not have a multiplicative inverse in Z15. Can we say the same about, say, 10? Well, 10 and 15, their GCD is 5. It's not equal to 1. 10 and 15 are not relatively prime, and we saw that 10 does not have a multiplicative inverse in Z15. So here is our conjecture based on these examples. So we'll let A be an element of Zm. For example, 4 is an element of Z15. If A and M are relatively prime, meaning their GCD is 1, then A does have a multiplicative inverse in Zm. Conversely, if A and M are not relatively prime, their GCD is not equal to 1, then A does not have a multiplicative inverse in Zm. Now, this is a powerful conjecture because, as I said, it's much easier to determine whether, say 8 and 15 are relatively prime than try to figure out a multiplicative inverse for each of these elements in Z15. So we can determine whether an element has a multiplicative inverse in Zm with in a much less computational way. Now, the proof of this conjecture is in the chapter 4 reading, so I will leave it up to you to read the proof carefully on your own. But for now, that's the end of this lesson, and I will see you next time.